applications now 3D printing is limited only for some particular applications where high strength is required. The 3D printing is not used. So when come this actually the 3D printing for all, that is more important before because the experts are there, they will be explaining today and tomorrow about the 3D printing. Let me touch upon 3D printing for all. All of you are aware today. There is one word called do it yourself. Do it yourself. DIY. This DIY concept, what is happening is with the DIY concept, there are apps are going to come and we can create our 3D model. Suppose you want your frame for the goggle, you can create our 3D model and there is a centralized 3D printing machine is available. You can send it to the machine and even CAD/CAM software is going to replace the apps. That is the latest technology. That is what people are expecting today. And with the app, you'll have an app in your probably in your mobile and computer. And with the app, you can create whatever funny part you want and send it to a 3D printing machine at a centralized location and get the component whatever you want. You can have your own spectacles. You can have anything, any item. Even jewelry also, you can have your own imitation jewelry. These all the things are possible. That is now today. That is how the 3D technology is useful for the society. And one more thing is now in medical applications, particularly the medical applications where the joints and other bones and other things are, particularly the tooth. The teeth, what they are doing, scanning, and then they are building up with the 3D printing, and they are able to do it. So this kind of various things are coming. But one thing I want to tell you is almost all the colleges today they are having the 3D printing, particularly the FDM machine. In Hyderabad, I think every college is having this. This giving a sort of facility for the students. They imagine something, some sort of design they imagine, and they are able to build that image and see physically that whatever they are thinking is actually useful for this whatever innovation they are going to do. So this kind of things now what is happening, they are developing the design thinking and innovation in the minds of the people. That's one advantage. This is also one advantage. It is no more it's just used for industry, but also used for the public. That is how the 3D printing for all is a very good and very good topic today. And one more thing, this is actually a additive process. Subtractive process, what happens is you have to remove the material. But this additive process, because additive process, the scrap is very less. Because the scrap is very less, you are able to meet the environmental requirements also and circular economy. These all the things now you are able to meet, and this is a very, very good subject. I feel, the organizers have selected a very good subject. I am very happy that I am able to, participate in this meeting. And I once again compliment the organizers for selecting this topic, wonderful topic, 3D printing for all. 3D printing for all. I am really, very, very, what is that, fascinating the sentence, 3D printing for all. So with these few words, I once again welcome all of you for this wonderful program, and I hope you will continue today and tomorrow also, and learn from the experts. They are going to deliver the lecture on this 3D printing and benefit for yourself. Thank you very much for giving me this opportunity. Thank you, sir.
Thank you, sir. Thank you for your inspiring and insightful address. Now I request Professor Uday Shankar Ballari, Honorary Secretary, IIT Kalburgi Local Center, to kindly address the gathering. Sir.
Good evening, everyone. Hello, it's audible, sir? Yeah. Good evening. On behalf of Institution of Engineers, Kalburgi Local Center, I extend a warm welcome to all the participants. So actually, our chairman was about to address this one. So in his absence here, I, Uday Shankar Ballari, Associate Professor, PD College of Engineering, would like to give the keynote here. So today's webinar on essentials of 3D printing for everyone aims to provide a clear and accessible understanding of one of the most transformative technologies in modern manufacturing. 3D printing or additive manufacturing enables the creation of complex components layer by layer, offering greater design flexibility, reduced material wastage, and rapid prototyping capabilities. This session is designed to benefit students, academicians, and professionals by giving them a strong foundation in the fundamentals and applications of 3D printing. We hope this initiative contributes to knowledge sharing and inspires innovation among all participants. Thank you. Thank you, sir.
Thank you, sir, for your valuable words. Now, it is the time to introduce our esteemed speaker for today's session, Dr. Mallikarjun. Mallikarjun, sir.
Yeah,
Dr.
I can
Mallikarjun currently working as an assistant professor in the Department of Production Engineering, National Institute of Technology, Tiruchirappalli. Before he joined NITT, he served as an assistant professor from August 2019 to October 2020 in the Mechanical Engineering Department at Amrita Vishwa Vidyapeetham, Coimbatore. He received his PhD in 2020 from National Institute of Technology, Karnataka, Surathkal, in the additive manufacturing laboratory at NIT TDK. He has published several peer-reviewed journals, book chapters, full papers, and abstract presentation. In March 2026, under the guidance, the team secured second place in the International Global Power IQ University Challenge, winning a cash prize of €2,500. He had an excellent academic career, getting his undergraduate degree in mechanical engineering with first class with distinction from Khaja Bandha Nawaz College of Engineering, affiliated to VTU. He has a second topper in the B final year. Dr. Mallikarjun also won a second prize for a technical paper presentation during his undergraduate study. He did MTech from MS Ramaya Institute of Technology, Bengaluru, with first class and distinction. He carried out MTech project at Gas Turbine Research Establishment, Bangalore, on reverse engineering and rapid prototyping of turbochargers impeller. For his MTech project, he received funding from the Karnataka State Council for Science and Technology under the 36 Series Student Project Program. Now, without much delay, so I request the today's session speaker, Dr. Mallikarjun, to take over this session.
Okay, so thank you for the introduction. So can you please confirm my PPT is visible?
Yeah, sir.
Yeah, great. Okay, so I hope everyone, they can see my PPT. So title of the today topic, advances in FDM 3D printing. And before I start my presentation on this topic, I would like to thank all the panelists who are here today. And I also would like to thank for the invitation Dr. Vishadat Koyer, because he is the one who invited to us. And would like to thank Dr. Sangmish, who is present today. So due to some technical reasons, we swapped the talk. And good evening, one and all. So let us start. So if any technical glitch, please stop in between, or any questions, we may keep it at the end of the presentation so that I can take all. So otherwise, someone is really want to, have the question, they can stop me in between. Thank you. Yeah. So yeah, title of the presentation, Advance in FDM 3D printing. So this is the outline of the presentation. I'll be talking conventional manufacturing briefly, additive manufacturing briefly, workflow and additive manufacturing, and what are the application of AM, ASTM classification of AM. And I'll be in detailing about metal extrusion, that is introduction to FDM, flow diagram of FDM, and what are the filaments are used in FDM technology. Importantly, there are some work spot we are trying to print using our FDM printer in my lab. So we are when you print a new metal system, we always have some problems. Challenges will be there. So those challenges I'll be discussing. Followed by I have two case studies. So what actually how research we are doing with respect to the FDM technology in our lab, I'll be discussing elaborately. And finally, the future of FDM 3D printing and conclusion. So this is the plan of this today presentation. Yeah. So you might have seen these product portfolio. You might have seen, aeroplane, car, laptop, rocket, motorbike, bicycle, cell phone, whatnot. Now the question is, let us talk about aeroplane. When you talk about aeroplane, it's required more than 6 million parts. So recently, there's an accident in Gujarat. Many people have died and one person was, able to survive. So that Boeing Dreamliner has more than 6 million parts. So now the question is, what are those parts? What are the material they're used? What are the processing method they used to make those components? Now, similarly goes to the car. When you talk about the car, it's required more than 15,000 parts. What are the new cars are coming nowadays? Even it's required more than that. Then again, the same question: how they're fabricating, what material they're using. So so that's a need to understand something. So similarly goes to the laptop, the rocket, bicycle, motorbike, cell phone, right? Yeah. So then, what are the conventional manufacturing process? As I said in the first slide, so there are various methods that are used. So from the, the beginning, like we had casting, forming, joining, subtractive, non-traditional machining. However, so in this technology, the subtractive manufacturing process, that is machining, is predominantly dominated compared to all this technology to get the final component. Now there was a paradigm shift to the technology happened in the year of 1987. So until then, it was dominated machining, as I said. So CNC machine to the SLA machine. In the year of 1987, the first SLA machine was introduced in USA. So you can see in this, the slide, we have this desktop computer, old desktop computer, and we have here right side SLA machine. So this machine was called as stereolithography apparatus. So that time used to use it for only for the prototype purpose. That is only the function of this 3D printer. But before that, let us understand what are the industrial revolution we have seen so far. All right, the first industrial revolutions happened in the year of 1784. So that time, the 1.0, the buzzwords are like water, steam, the coal. And what was happening in that 1.0? So majorly, the people started using the equipments tools. It means and to the equipments and manual work to the mechanization. That was happened industry 1.0. Then when you look at the industry 2.0, that is second industrial revolution. So it was majorly on electrical energy usage and mass production. So the mass production is influenced by slaughterhouse, where they're hanging the buffaloes for cutting. The same thing the Henry Ford watched that slaughterhouse and he implemented into their car production. So in that time, the industry 2.0. So and most of the cars were made from Henry. So that's how the industry 2.0 come into picture. So then we move on to the industry 3.0, that is third industrial revolution, where we have witnessed many things so far. So electronics, CNC, IT, right, whatnot. So the PLC, it has started in the year of 1969. It went till 2011. So in 2011, there's a one annual fair in Germany. So every year it used to happen in European countries. So they announced in 2011 Industry 4.0. That's how this emergence of Industry 4.0, what you're talking today, where we have all these robots, machine learning, augmented reality, virtual reality, big data, cybersecurity, autonomous robots, automated guided vehicles, simulation, Internet of Things, IIoT, and whatnot. We have plenty of various components in Industry 4.0. Among them, this additive manufacturing or 3D printing is one of the component in Industry 4.0. That is the takeaway from this slide. Yeah. So then, what is additive manufacturing? So definitely, Dr. Sangmesh is going to discuss the basics in tomorrow the talk. I'll just quickly, wrap it up what exactly it is according to the ASTM F42 Committee 2009. Now, what was happening? So the process by which digital 3D design data is used to build up a component in layers by depositing material. This is a definition according to the ASTM F42 Committee. So what was happening that time? Geographically across the globe, the machines are developing, the invention is happening. So they used to call different names. As as I said, in the year of 1987, the first machine SLA, they used to call rapid prototyping, and different digital manufacturing, desktop manufacturing, solid freeform fabrication. So like that, the different names were there. And to avoid the confusion, in 2009, so they called additive manufacturing is the standard name and also commonly called as 3D printing. What are the other names I just said? All falls under the umbrella of this additive manufacturing. There are several techniques like as Sir Satyanan sir said. So we have SLM, we have DMLS, we have lens, we have FDM, we have binder jetting, metal jetting, whatnot. There are several techniques that exist today. So applications are limitless in the sense, we can use various sectors like, aerospace, automotive, apparels, fashion, jewelry, whatnot. I'm going to discuss exclusively on that, application slide. And range of materials. It's not limited to only metals or alloys. It can be used for the elastomer. It can be used for the tissue engineering. It can be used for the concrete. It can be used for the apparels. We can use for the gold, whatnot. The plenty of materials can be used using this technology. And it exists in the nature. If you see stone and bricks masonry, if olden days, if you go to village or some port, you have this kind of arrangement where they're keeping stone one over the another. Right. So the similar thing is happening with respect to 3D printing as well. And recently you can see everywhere where the construction is happening, houses are building. So what they do, they'll put a concrete and they'll put a brick, they overlay the concrete again, they put the brick. So essentially what is happening here? So it's a layer by layer deposition is happening. Layer by layer construction is happening. So that is what the additive manufacturing. So then, so we have several techniques. So this is a generic process plan. Steps are used to building any AM component in any AM machine. The first thing we require the CAD model. So it doesn't matter. So what are the idea you have? What are the proof of concept you have? You must have the CAD model for this technology. So what is a CAD model? We know that, right? So we have different softwares like CATIA, Autodesk Inventor. So we have Unigraphics, SolidWorks, right? The Creo. So Google SketchUp, whatnot, Blender, the various solid modeling softwares we have. So what are the idea concept you have? You have to make a CAD model. So once you have the CAD model, that is solid model, so then you have to convert into STL file. Why? Because that is a de facto file format for the additive manufacturing. But however, the recent improvement in the technology we have, like OBJ, AMF, 3MF, VRML, the various other file format also acceptable. But STL is one of the standard file format, that is standard triangulation language, which is being used. So what it does actually, what is the solid model you had, it's going to represent a surface as it using the many triangles. That's what you're going to do it. If you delete a triangle, you can see inside it's going to be open, it's going to be hollow, right? So that's what the STL. So it's going to be very light size and easy to use it for the additive manufacturing process. So once you have the STL file, then you have to load into the slicing software. What is slicing software? So let us take an example, like you have an apple. So what you want to do, you're going to cut it to pieces to have it. Similarly, so now what we are trying to do, we have the 3D that we're cutting into 2D cross-sectional images, thin layers. So how we are doing that using the software. So Cura is one of the commonly used software across the globe because it's open source software. But we have several slicing softwares nowadays, Octoprint, KISSlicer, right? So then nowadays, what are the machine they're selling? The own company is having their own slicing software. So that's how things are coming up. So essentially, we have to slice that 3D into the 2D cross-sectional layers. That's what essentially is happening. That's a mathematical description. We can do it by defining the various process parameters like layer height, speed. So then you can have orientation, all those things. So once you define that, you can slice it. You're going to have a G code. So G code, what is this G code? Already we know that in CNC part programming, what we do. So any drilling, milling, what are the, you want to make it operations. So you have to write a part programming. The similar thing which is generating a tool path using the software called Cura. So that G code will be loaded into the machine. 7 categories according to the HTML. It may be FDM, it may be SLM, it may be lens. What are the technique you have? You can load into that machine. So it will start building layer by layer. That's what happens in the additive manufacturing process. Once it is built the layer by layer, allow for the cooling, then you're going to take out, you'll go for the post processing. What is the post processing? We'll be taking out the superstructure, we'll be improving the surface finish and putting the color and all those things. So finally you're going to have the prototype or a functional part. These are the generic process steps which are involved in building any AM technique. So that's what we have to understand, right? So now applications. So you can see this slide. So when it was introduced, that time only used for the prototyping purpose. Since its inception, so it was used only for the since its inception it has exponential growth. We have seen it, but when it was introduced, only used for the prototyping purpose. So later that casting, tooling, automotive, aerospace, then we have reached we're going to have full body organs by 2030. What it means, see, across the globe, the many people will die, but no one is ready to donate their organs to the person who required, the patient who required. Now there is a need to cater this requirement. What 3D printing can do, that is bioprinting. So use the tills, you can tissues, use the print, bioprinting. You can use the tissue material, that you can print the organs like heart, liver, kidney, and whatever we have. And people who want, we can we can implant into this organ so that you can save the patient. That is what the motto. It is expected by 2030. It may take maybe less or more time. So you can expect these things happen in future. And when you talk about this additive manufacturing application, it is spread into different sectors. It may be design, it may be engineering, analysis and planning, applications like home appliances, biomedical, automotive, jewelry, consumer electronics, aerospace, right? Whatnot. It is spread into various sectors. That's the application of the additive manufacturing since its inception. These are some particular applications. But you can see during COVID, the people are trying to print the mask using 3D printing, and you can see this is 3D bio printing to create the beating heart, beating human heart. You can see the prototype. They're actually trying to have the beat like a actual what we have. So that's a prototype. The nuclear bicycle, right? Another example in the biomedical, you can see this is using SLA machine or SLA machine where you're going to use the resin. This particular component, we can see clear crystal where the bones are there and where the brain is there. This kind of prototype will help doctors and medical students to understand better where the disease it is, where the damage it is. It is none of the other technology can give this information. Now assume that some crack is there, some damage is there, easily they can understand what is happening. So there is always when some surgery happens, doctor always say that we will take a call during the open incision. When they open, they can understand better what is the problem. So those kind of problems can be avoided if we can have this kind of prototypes to the doctors and other doctors and students. So yeah, so then it's not only limited to the medical prototypes, and also food printers where you can print the chocolate, ice creams, meat, right, the pizza, burger. And even you can expect in future every hospital might have this printer where they can print the implant, where they can print the custom specific patient food requirement, vitamins, proteins, and XY. So like that you can expect in future as well. And the concrete 3D printer, so you might have heard about printing homes, post office, buildings and shelters, bus shelters and all those things. So that's how the applications exist with respect to the additive manufacturing. Yeah. So then the classification of additive manufacturing. So far, according to the ASTM F2792 standard, there are 7 families of additive manufacturing. So there are other techniques that exist, but according to the ASTM, these are 7 families. The first is white photopolymerization, and second is powder bed fusion, and third is binder jetting and metal jetting, sheet lamination, material extrusion. This is where I'm going to have in detail explanation in the coming slides. And direct energy deposition and hybrid manufacturing. I think Satyanan sir was telling about this in the introduction, hybrid manufacturing, where the new faculty has come from Canada. So what happens in the hybrid manufacturing? Assume that I have a lens machine or directed energy deposition machine where I'm going to try to print the component. What is the part I'm printing? It's not the final component. Either I have to go for the removing superstructure or machining to obtain the required surface finish, require the dimensions. Right. So that is, you have to remove the part and take it to the milling, drilling, whatever it is, then you have to perform. To avoid that time, so in the same system, we'll be having the machining option, so that once the deposition is done, that tool will be get changed, head will be get changed, and you can perform the machining and what are the other options. That's what the hybrid manufacturing. So that will help us to finish the component faster. That's the whole idea of having that. And there are some new technologies like melt manufacturing, 3D bioprinting, XYZ. Yeah. So then A materials, these A materials, A materials, like you can see this, this slide where we have different technology around to this feedstock or materials like powder, wire, sheet, rods, dispersion, filament, and pellet. So in this talk, I'll be looking at this metal filament fused deposition modeling. And these are various materials. You can see polymers in that. How many materials are there? Metals, the various materials. So then ceramics, composites, other materials, whatnot. There, the plenty of materials can be used in additive manufacturing. Yeah. Now we are into the topic metal extrusion. So I'll be concentrating on only the filament based. So because in that we have different techniques, granules and all those things. So what is this metal extrusion additive manufacturing? All right. So according to the ASTM 52900 2015, material extrusion is umbrella term for the 3D printing processes, in which material is selectively dispensed through the nozzle or orifice to build the parts. In simple sense, you can say that when you have a hot glue gun, right, what you does, just press it, so glue will come out. Correct. The same thing which is happening with respect to the material extrusion. We have a nozzle, so in that wire is fed where it maintains certain temperature. You're going to press and you're going to have a dispensing of the bead material for the printing. So under this category, fused deposition modeling is a famous technology, and Stratus Inc. company developed this metal extrusion based FDM technology. So still in the market, they are one of the tough company, a tough competitor to other companies who are exist in the FDM technology. So it was introduced first FDM 3D printer in the early 1992. The later company developed several models and sold across the globe. So there are two categories of FDM machines. Only for the Stratus I'm talking, FDM series and concept modelers. And these models cater various needs and build and for different materials accuracy, etc. of FDM machines who produced Stratus Inc. However, this technology and makers, so this technology also called as fused filament fabrication, fused deposition modeling, rover casting, fused granular fabrication. So in this, what is happening, where instead of the filament, so we'll be having the granules, we're going to put in the upper. So the same thing, rest, deposition of layer by layer happens. The players are makers of this FDM technology like MakerBot, 3D Systems, Fabster, Envision Tech, Alfie Object, Bamboo, Pro, 3D, then Stratasys, etc. So these are the makers of this FDM, but there are plenty of players you can see across the globe now. It's not limited to only these 8 the makers. Anyway, so how this works actually, how this FDM process works. So you can see the schematic, simple schematic where we have the build platform, or that we're going to build the component or any specimens or coupons. So this build platform is having the z-axis. It means it can move up and down, and this nozzle which is having x and y movement. So in the filament spools, we have two filaments. One is for the superstructure, that is orange color, and other is for the actual building the component. So what is happening when you start the printing? So these two filament is fed according to the G code what you generated. It will come into this nozzle head. There will be some rollers. It will fed into the nozzle. Nozzle is maintained certain temperature based on the melting point of that material. So it's going to melt and going to dispense material through the nozzle and start building bead by bead, followed by layer deposition. That's what's going to happen in the FDM process, deposition. You can see the animation explain the same thing. It's depositing into the cup, right? So that's the simple explanation for this FDM process, how it works. Yeah, there is a FDM movie. I just quickly play, and I'll try to have voiceover if it's not visible. Yeah.
FDM is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin red light spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts, including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
Yeah, so that's about FDM, process. And yeah, so this is a flow diagram for the FDM. So as we see in generic process plan, similar to that, very specific to FDM technology. So definitely we have to have the CAD modeling, and that can be using software, or you can use the reverse engine. Like maybe if we talk about the biomedical, where you have to have CT scan or MRI data, so that will be processed to have a CAD model, or any reverse engine scanner you can use to scan any component, any the old the products which doesn't have the CAD model. You can do the reverse engineer. You're going to have a CAD model. Once you have the CAD model, you can convert STL file, and you have to slice it using slicing software. Then that G code will be loaded into the machine for the printing FDM machine. And once it's printed, you're going to take out. Then you'll be doing the post processing, maybe removing the superstructure, finishing, painting, XYZ. Then you're going to have a final component. So this is what the FDM printing flow diagram. And what are the types of FDM printers? All right. So there are the 4 classifications. So first one is the Cartesian, and delta, polar, Oberticon. So this blue color which indicates the build volume of this printer. So, but if you look at among 4, the first one, that's the Cartesian based, will be commonly used technology across the globe, and even it comes from it is available at a cost of 10,000 rupees onward. So if you can see Amazon, it is available at 10 to 15,000 rupees. You're going to get a printer. So that's how the cost-effective 3D print, you can see none other than any other machines, like maybe some DLP also it is available, but this is one of the lowest cost printers are available. And anyway, these are the 4 types you can expect. And the 4th one, importantly, the Roboticon, generally used to build larger size the components. In our department, there's one professor, he did recently one project to the DRDO, where they built this machine for DRDO, where they want to print the composite the material of large size products. That's successfully they did and delivered to the DRDO. So that's how things are happening, and it's commonly used in concrete 3D printing as well. Anyway, now what are the feedstock in the FDM? So there are various material. Basically they start with the PL and ABS, and commonly used nowadays also. But apart from that, you have the P, Kevlar, LDP, STV, PETZ, carbon fiber, whatnot. The plenty of materials are available as a feedback for the this FDM technology. So if we talk about the wire, that's the filaments. So it comes with the 1.75 or 2.85 millimeter diameter, based on the machine you have. So it will be accepted the 1.75, 2.85 diameter of filaments. And also there are some FGP, as I said, fused granulation techniques, so where it accepts the pellets. So will be upper, it will be feeding that, and the rest will be, the same thing is going to happen as the filament machine. Yeah. So then FDM process parameters. So if you take an additive manufacturing, as we discussed in the classification, all machines have the various process parameter. So these process parameters are specific to the FDM machine, and we have like a nozzle. Just quick explanation, like so we need to maintain certain temperature to the nozzle. For example, you want to print a PLA using FDM technology. The rated temperature is 190 to 220 degrees centigrade. So that's the range you have to give, so that once the PLA material enters to the rollers, so it will be melting and properly dispensing into the substrate or into the build plate platform. And bed temperature also recommended for 40 to 60 degrees centigrade. So this kind of the temperature is different for the different material. ABS is different, SDP is different, LDP is different, PC is different. So each material has different melting temperature, bed temperature. So that will be, if you're buying filament, it will be given, or if you're developing the new metal system, then you have to do DSC, TG and all those things to confirm all these things. Then let us talk about the layer height. In the layer height, what is happening? So if you increase the layer height, it will take more time, but you're going to have a good surface finish and as well as good mechanical properties. But if you're going with the higher layer height, then you have to lose these properties. Similarly goes to the infill density. So none of the conventional methods can give this kind of infill density percentage filling, right? So 10%, 25%, 50%, under percent, 80%, whatever it is. So based on type of component you have, right, you can fill this, you can save the material, or you can have under percent also if it is required a very good strength, or you are looking at only a prototype, then you can go with the 10%, even lesser also. right? So that's how you can say the material. And infill pattern, we have grid, gyroid, honeycomb, triangles, cubic, rectilinear, right? The plenty of infill patterns are available, and it's also influenced by the biomimetic. There's a lot of work is exist on infill patterns in the literature. The flow rate, the viscosity is very important. So then build orientation. So in the slicing software, we must aware of the what kind of orientation is required, because unnecessarily you have to increase the metal consumption and time and all those things. The proper orientation not only finish the good surface finish, reduce the print time, so also reduces the the metal consumption and the time requirement, improve the strength and all those things. And the support structure is one of the important aspect in 3D printing, because we'll be printing the complex overhanging components. So when you have those kind of stuff like undercut overhanging, so we need to give the support structure. So this is where the slicer come into picture, how to avoid these things so that we can reduce the support structure and all those things. Even though we have the overhanging and bridges and all those things, so without support structure always recommended, but in certain cases we cannot avoid. If you're giving also, how least you can give, so based on the orientation matters. Then cooling settings and nozzle size depends on the machine, right? So it starts from 0.1, even lesser also in micro printing. So 0.2, 0.2, 0.3, 0.6, 0.8, 1, right? Within less than 1, generally, printings are available. So then raster angle also is very important to have the tensile strength, 0 degree, 45 degree, 90 degree. And I have a example for that I'm going to discuss. Then brim and skirt in the starting of the printing, we're going to check whether, proper printing is happening or not. And other process parameters. These are the major process parameter we will be looking at when you go for the printing of the material. Anyway, so when you start printing, there will be some defects. It's not like that. You have a filament, you have a printer, and you have a camera. Just load it, and you're going to get a component. No, nothing like that. So there will be some problems. Like if you look at this figure, we have warpace. What is happening here? So during the printing, you have we have to give bed temperature. Assume that bed temperature is not sufficient. Gradients are going to play a significant role to have this warpace or delamination, right? So the entire product will going to warp, and whatever printed maybe 5 hours or 6 hours or 1 day, that component going to lose. So this kind of error come into picture. Then you have element foot, you have the layer shifting, you have the stringing, you have the jet wobbling, the curling, then layer separation. All these defects, even few I'm mentioning, even more defects you can expect in the Debden printed parts. I have exclusive case studies challenges for this. I'm going to discuss in coming slides. Yeah. So this is the 3D printer we have in our lab, and the specification of this 3D printer. So it is MD400D and purchased under a seed grant. So when I joined, they give some fund for us to buy this. I purchased under that seed grant, and this is specification of that. Yeah. So this is a concrete 3D printer nozzle. So you can see the first figure where we have like a bulge diameter and the layer shifting. So you can see almost it was finished, I think 70%. So then we could see the layer shifting of this the component. It means after 5, maybe 4.5 hours, where we are going to have a layer shifting. So it means we are wasting the time, material, and all those things, right? So now, what was the problem for this the failing, and how we have finished that? You can see in this the second image. These are finished parts of EBS and PLA. So we're able to print it properly. The problem was it was performed the Z-axis calibration. It means the build platform what we have, that calibration was the issue, and it's deviating from that actual movement. That was the cause of concern for that, and we did the recalibration, and it was successfully printed this printer nozzle. So one thing I want to highlight here, this printer nozzle was part of the one of the project concrete 3D printer. So where we have a pump, and this is one of the part of it. So we are printing for that, and this issue were there multiple times. We printed, finally we achieved it, and for that printer we received an award at NIT Warangal with a cash prize of 40,000. Yeah. So then the same concrete 3D printer, the piston part, you can see that this is the failed part. So almost we have finished around 70% of the part, and nozzle shifted after this layer. So this was happening frequently. So at particular location only the nozzle getting shifted when we are printing this component. We did multiple times and same error was came, and we are wondering what was happening. Then we tried to understand the this HCl file, recycling and all those things, but still it's coming. The problem was what we noticed, and if you see the this AM process of building, right, generic process plan, what we have, first you're supposed to have the CAD model, then you have to convert it to HCl file, right? So during this transition from CAD model, that is a solid model, to the HCl file, so assume that maybe due to some error in the solid model, so or when you're converting the HCl file, because the tessellation language surface representation, right, maybe you have a the complex geometry, some XYZ, and you are unable to convert the proper HTML file. You're unable to have the proper HTML file. So generally what happens actually, once you convert HTML file, there are softwares like Netfab. So they load the HTML file and try to check it. Is there any overlapping? Is there any missing sets and all those things? There are some errors will be there when you convert one form to another form of file format, right? The same thing was happened here. Then we identified, we do the correction. So then ultimately we are able to print this component. This is the finished part of the piston for the concrete 3D printer. So like that, we tried NDT sample for using PETCF. We can see that warpage which is happening, and also stringing and all those things, and filament bulging, right, for this PETCF. The problem was this warpage and bulge is due to the bed temperature and the poor addition of the build platform. So you should have the proper bed temperature also to avoid this bulging and warpage of the sample. So finally, you have printed the proper one after changing the bed temperature. So tensile test, TPU is one of the elastomer and highly flexible material used for many applications. So we tried to print this material, virgin TPU material, with this process parameter. It was this sample was taking 28 minutes, but you can see there are some issues like poor surface finish and stringing and all those things which is happening. So the remedy for this was like adjusting the nozzle temperature. That was the issue, and also recalibration of the printer was necessary, so that we have obtained the final finished tensile samples with good surface finish of this TPU material. So like that, so then as I said, raster, the width or raster angle, it's one of the important process parameter in FDM technology. So then we tried of printing this TPU with a superstructure of PVA, and even the TPU as a superstructure along with the core printing at 45 degree. So we have printed successfully 0 degree, we have printed successfully 90 degree, but what was happening at 45 degree, we are unable to print it. You can see the first one is the manual support, what we have given, and second is the tree support. So in that slicing software, you have different supports actually. So we have tried it, and even we use this PVA. So PVA is the supporting material. If you dip into the water, it's going to dissolve very easily. So that's what the PVA material is, very expensive filament. So we have tried that one. So you can see what is happening. So we are completely unable to print it. So after we are stopping, this is the superstructure and this is the actual component, 45 degree. So you can see this is superstructure and this is the tensile sample. So this is the 45 degree. So stringing and all those things, all the errors are coming. But still we unable to solve this problem for TPU material. We have printed other materials of, like a PLA, ABS, carbon fiber with a different combination. But when you talk about TPU, are unable to print it to 45 degree, unable to rectify it. We tried many ways of printing it. So I think we'll try to print that as well in future. Anyway, so then another the challenge was like the micro tensile sample. So it was tried PETCF sample. You can see there is some irregular surface texture what could see on the micro tensile sample when you're trying to print the PETCF. So it was taking just 6 minutes, but we are not getting the good micro tensile sample. So, but we identify the issues like the cleaning nozzle, because sometimes what happens when you change the different materials, there will be some debris of particles inside the particular the nozzle, right? So use the e-copper to print it. So those copper particles were there inside the nozzle. So then we cleaned and increased the temperature. So then extrusion become consistent. Then we are able to print successfully these microtensile sample of the PETCF. So that's how we have tried it. So then you can see, sorry, I think this I think is disturbing. Yeah. Okay. Yeah, great. So this is a rocket nose cone prototype. So in machine, this is one of the largest component we have printed using FDM technology. So it took 1 day 57 minutes without interruption, and these are the other process condition. So this rocket nose was printed for one of my colleague student. They participated in ISRO challenge. So to understand how the machine works, you have printed it has come very good in the first printing itself, and you can see very good surface finish, and what are we expected, they wanted, actually we are able to print it in one shot. So that's how we tried the printing using our printer. So that's a different activities we have tried using FDM technology. Then similarly, we are trying to print the membranes. Membranes are used in various purpose for the filtering, and e-copper, ABS, PLA, TPU. So diameter is around 75 millimeter and the thickness is 0.3 millimeter. So in that only 2-3 the layers of printing for different layers. So we are able to print it. So idea is that here to have the different porosity, so that the water the passing is happening, the different particles, water, chemical, whatever it is, that can be prevented. So that's the whole idea of printing these membranes. One of my colleague in chemical engineering have tried for him. So then methods for producing the filament. Those are the challenges with respect to the FDM, what we tried for different materials and components. So now the actual work, I just want to start here with the filaments, right? When you talk about the filament for the FDM, so we'll be using different methods like melt extrusion, compounding and extrusion, single screw extrusion, twin screw extrusion, recycling, and chemical methods. These are the common methods you can see when you talk about filament production for the FDM. So I'll not go in detail this technology. So now let us see the case study one, where we use the single screw extrusion of TPU composite for filaments. So we had the TPU material, the filament pellets, and also we have purchased the PLA, and we try to mix some composition, try to produce the TPU PLA composites. So now what is this TPU? So TPU is known for high flexibility, elastic recovery toughness, and abrasion resistance. So ideal for various applications, like in say football, wrist brace, biomedical applications. But the problem with the TPU is the strength and the toughness. When you talk about the PLA materials, it has high toughness and strength compared to the TPU, but it's a brittleness, right? But it also used for the various purposes. Now, these two materials were selected to produce the filament. Okay, so now we have the PLA pellets, we have the TPU pellets. All right, so you purchase from the rightful vendor. Then we use this single screw extruder, RP extruder machine we have in mechanical engineering department, one of my colleague. So he has given this facility for extrusion of this TPU PLA composite, and after the various permutation combination, we're able to obtain this TPU PLA composite. So different combinations were tried, like 90% and 10%, 80%, 20%, 70%, 30%, something like that. And we're able to obtain these filaments what we expected, right? So then you can see these are wounded TPU PLA composites, and these filaments again used in the FDM printer and printed the compression samples. So this is how we are able to make a new metal system, that is TPU PLA composites. Okay, let us see some results on this. Yeah, so then we took the filaments what we extruded after the single screw extrusion, and we try to understand how temperature is degrading, right, through the TG and DTG results of this TPU PLA composite filaments what we extruded. And the mass loss was higher at approximately 420 degrees centigrade, right? And TPU undergoes a maximum loss of 370, and TPU and PLA's loss is 420 degrees centigrade. So this kind of knowledge is very important because we have to give the proper bed temperature, you have to give the proper nozzle temperature. That's how important when you go for printing with the FDM. Now there's melt flow index, so where how the flow of the liquid flow of the liquid material. So that's how help us to understand through the MFI. So pure TPU demonstrate high at MFI 19.709 gram per 10 minute. If this composite what we prepared, so it was 3.099 gram per 10 minute. So that's what the knowledge we have gathered through the MFI. So then we did the hardness of this TPU and TPU PLA composite. So TPU PLA composite was enhanced due to the addition of the PLA. So that's the result we have got it. So but I'm not presenting the compression samples what we printed TPU PLA because we are having some undisclosable thing on that. So we are submit to the paper. So right now I'm not showing any results on that. What are the 3D printed samples we did to single screw extruder. Anyway, now the case study 2, novel in situ preparation and printing of TPU composites. Right now, the previous case study, what it has been explained, where we have a particular screw, extruder. So you have to add the pellets, you have to perform some process parameter, then you have to obtain the filaments for the FDM 3D printer. But what we have tried here using that, what are the FDM printer we have in our lab. So there the filament is CPU, another filament is a PLA. We have the both extruder. So we are using both extruder and you're trying to print it. It means we are printing the component, composites, TPU PLA composites in situ. That is the idea of the second case, right? You can see clearly this schematic explains this alternative layer fabrication of TPU PLA composites. So this is the spool where you have the PLA. This is a spool where we have the TPU. That's the red in color. Now we have the two nozzles in that printer. So what happens actually, the first layer will be printed by the PLA and second layer will be printed by the TPU. Second layer will be second extruder will be printed by the TPU. So that's what happening when we talk about alternative layer fabrication for making the TPU PLA composite material. All right, so this you can see the schematic again. One nozzle one is printing, that's a green color PLA, and second nozzle is idle. Once it is done, and second nozzle will come and print for the TPU. That's what happening. And this is the micro tensile sample. So the HM standard. So 38 overall length and 15.9 width and 4.8 is the gauge width, and gauge length is 22.2 and the thickness of 3 millimeter. That's the dimension we have printed. So we have used the various process parameter like infill type, trihexagon, archimedean, 3D honeycomb, octagram, spiral, rectilinear. So then we varied the infill density. So 20%, 40%, 60%, 80%, 100%. We want to know how the mechanical properties are influenced when you print alternative layer of TP and PLA on mechanical property. That was the whole idea. And these are the constant process parameter was used to print these 27 samples, L27, layer height is 0.1, print temperature is 220 degrees centigrade, bed temperature is 60 degrees centigrade. Now we can see, so using that machine, what we had, and we have printed 27 samples, that is L27. This is the infill pattern, and you have the infill percentage. So this white color, what you are seeing, so these are the, alternative layered micro tensile samples was printed. Anyway, now we did the tensile test of these samples, right, for the trihexagon to the rectilinear. So what is the takeaway from this slide is that 3D honeycomb structure infill pattern is giving the better results compared to the other infill patterns, right? Why? What is the reason? That we found that through the factography. So if you see this figure C, where we did the SEM, what is happening here? The fracture is happening through hook. It means before the fracture, inside the material is forming a hook kind of shape, and it's arresting the dislocation, and it's taking the more load compared to the other material. So that's how we are getting the good tensile properties in 3D honeycomb compared to the other material. So that you can understand cleanly here. So we did the tensile test for the TP and PLA virgin material and the TP PLA composite material. So here what you are seeing in this slide is the ultimate tensile stress alone. TP is 12.2 and PLA is 45.4. And you can see trihexagon, archimedean, 3D honeycomb, octagram, and rectilinear. Among these things, 3D honeycomb is better because as I explained, so what was happening. And similarly, we extracted the modulus. So modulus is 18.7 and PL is 2180. Now we can see, so in honeycomb is highest and followed by the trihexagon. So the same reason we can quote here. This is the takeaway, like the how infill patterns can influence the tensile strength properties. Yeah. So then almost we are coming to the closing. The future of fused deposition modeling 3D printing. So now what is the future of this FDM is that we are using ABS PLA, right? Then LDP, SDP, and all those things, the PC, the different materials they're trying, but they are now looking for the aerospace and biomedical applications like a PEEK, Ultem material, and even Kevlar and other materials. The recently, there is a one work also we're trying to do it. It may be surprising for you. So we are trying to print the stainless steel material using the same FDM technology. We have printed those samples. I'm not, revealing because of the patenting purpose. So we have printed the stainless steel where reinforced in the polymer. We are able to print using the same the FDM machine what we have, right? So it means the expensive one, more than 1 year is required to have a FDM metal printer. So the same thing we are trying to print using FDM machines. In future, you can see those kind of stuff is going to happen. So then in situ compounding and direct pellet printing. So instead of extrusion, right, that's time consuming. So what you can do, we can use this in situ compounding and direct pelleting. So that's where the granulars are happening, FGP. And your case study 2 also we have tried the same thing. So then, actually, I could not find any literature, whatever work I presented in the case study 2. So we are submitted for a good journal, hoping for the publication. And, that kind of work is going to happen. Then AI-based optimization process parameter, not only AI, so you can use machine learning like, what we have, random forest, SVM, and all those things. So one of the work where recently we published in IIT Madras, so in conference, which held my PhD student went and published, presented, and it is been under considered for the publication. So where we used machine learning, a different algorithm to predict the tensile strength properties. So what I explained, those things you can predict, right? Not only the tensile properties, you can predict the bending strength, you can predict the compression strength, and 4-5 mechanical properties are predicted, and we validate as well using experimental data. So that is kind of work you can do using FDM technology. Then shift from prototyping to the mass production. Currently, this FDM technology used for the prototyping plus functional parts also, but not for the mass production, but it can be used for the mass customization. So in future, you can expect a mass production. Now, just now I'm seeing, if you go and just Google it like FDM 3D printing technology and go to the news, you can expect some machines like 10x faster, 25x faster. So faster is very important because it's a layer by layer deposition. It's a slower build rate. It takes a lot of time. So we definitely required 25x, 50x faster 3D printing in FDM technology so that you can achieve the mass production. Then only we can have less cost products. Anyway, so large format 3D printers for automated and construction. Already in construction, they're printing the 2-story building, then bus shelters, and many things are happening, bridges and all those things. So large format is expected. Automated also where we can print the car body directly. There are some case studies they're printing part by part, but you can expect in future like the entire car body can be printed using 3D printer. That is possible. Sustainable and green manufacturing, of course, because unlike the subtractive manufacturing, here what we are trying to do it, we are adding the metal to get final component. But how we can expect, because of the government policies now, a lot of CO2 emissions can be reduced, and circular economy what you're talking. So this FDM technology will help us for the sustainable green manufacturing. How we can use extensively this technology towards it's a matters. So then the final the future of this FDM is that market witness. See, whatever you talk, market should be there, right? So according to the compound annual growth rate of 11.7% and valued at $6.3 billion in the year of 2024. And importantly, they expected to grow to reach $12.1 billion by 2030. It means just next 4 years, you can double this investment in the market. It means one can take the career in this FDM technology. You can do a startup, whatnot. So plenty of things can be done with respect to the FDM technology. That is what the market survey says that. Yeah. So conclusion, last slide, what we have, like additive manufacturing definitely a disruptive technology, widely accepted in the various sectors like aerospace, automotive, biomedical, passion, whatnot. The plenty of sectors we have, and FDM is one of the mostly used technology across the globe because it's a start. The printer at 10,000 rupees you can buy in Amazon also. But thing is that optimizing process parameter is essential, because when you are working with the new material system, this is very, very important. We cannot have new material and you can print like that. That is not possible. Then it can be used for the various applications as I suggested. And but the thing is that since the challenge what we noticed, like in between software stringing, warpage, XYZ, so it's limiting the the part fabrication FDM. The case study presents the conventional and widely used approach for the filament production. for FDM. But however, it increased the time and cost. In case study introduced the innovative approach where you can do the multi-material printing directly within the FDM system. So we can avoid that first step what we required for filament extrusion. So that reduces the time and cost which is going to incur for the filament production. And it opened the new possibilities for the part fabrication. Yeah, these are some references. And thank you. So I hope everyone able to hear my voice, and any questions I'm ready to take now.
So the participants are requested to post their questions in the chat box.
Voice speak.
Any questions, please post in the chat box, or I can maybe unmute and you can ask the question. I'm ready to answer. There are around 45 participants.
Yes, sir. Okay, sir. Now I will, first of all, thank you, sir, for that highly informative and engaging session. Now I will briefly summarize today's proceedings. We begin with an insightful welcome address by C.R.M. Satyanarayan, sir, emphasizing the importance of emerging manufacturing technologies. This was followed by the encouraging remarks by Professor Udayashankar Bellary, sir. From the session of Dr. Mallikarjun sir, we gained valuable insights into enabling the complex and high performance customized parts. And we also learned the advances in materials and processes expand applications and supports efficient low waste flexibility manufacturing. Overall, the session highlighted how advances in 3D printing enables complex customized components, expand applications through improved materials and processes, and support efficient, flexible, and sustainable manufacturing. We will now move to question and session. If anybody wants still have any questions, they can post their questions in the chat box or they can ask directly.
Yeah, so I have my email ID. So anyone really have the doubt, they can approach me. Even they can try for the part-time PhD, then internship. So currently, which is going on, BTech internship, MTech, right? So they can approach me via email.
Okay, sir. Kindly share your email ID in the chat box. If anybody wants, they can ask.
Yeah, definitely.
Okay, sir. As we come to the end of today's session, on behalf of IIT Kalburgi Local Center, I propose the vote of thanks. I sincerely thank our esteemed speaker, Dr. Mallikarjun sir, for his insightful session. My heartfelt gratitude to Dr. C.R.M. Satyanarayan sir for his welcome address, and Professor Udayashankar Bellary sir for his support and encouragement. I also thanks all the participants and organizing team for making this session successful. Thank you all. Have a pleasant evening. Thank you all once again. Have a wonderful evening. So we will conclude the session now, sir.
Thank you very much, sir. One last information to the participants. Those who want to apply for the participation certificate, they kindly register themselves and pay a small token of 300 rupees. They will get the certificate in their mail IDs within 3 to 5 days. Thank you.
Thank you. Thank you, sir.